Hello and welcome to Know the Heart of ICU. It's a new cardiac in-service education initiative offered by the Intensive Care Department in Letterkenny University Hospital. The first unit of our cardiac session is dysarrhythmia, and this unit is divided into two chapters. Chapter 1 is normal ECG and chapter 2 is abnormal ECGs or abnormal rhythms or dysarrhythmias. In the chapter 1, the learning outcomes are at the end of the session, you should be able to define what an electrocardiogram or an ECG or an EKG is. And you should be able to explain the conduction system of the heart, and you should be able to discuss the normal characteristics of waves, segments, and intervals of ECG, and you should be able to identify the normal ECG. When it comes to a formal definition, ECG is very complicated because according to Tora and Direction, ECG is a composite record of action potentials produced by all the heart muscle fibers during each heartbeat. I know it's kind of a technical jargon, it's full of physics jargons, but when it comes to a simpler explanation, it is a graphical recording of the electrical activity in the heart. So it's very simple. It's just a graphical recording. You're putting the electrodes on the patient and you're connecting to a machine, and the machine gives you a graphical recording of the electrical activity of the heart. So how this electricity is working in the heart? The heart, as you know, is a pump, is a muscular organ, and the heart has its own pacemaker. Usually SA node is a pacemaker, and how the electrical wiring of the heart works, how the electrical impulses is conducted from the pacemaker, that is your SA node, to the heart cells or heart muscle cells. There it comes to the conduction system. So there is an electrical wiring within the heart. In a normal scenario, in a normal ECG, the electrical impulses are produced by the sinoatrial node. That's a little group of tissues that lies just beneath, just below the your superior vena cava. And this SA node produces impulses, and that impulses needs to be taken to the muscles. So we have some interatrial bundles that takes the impulse from SA node to right and left atria, and we have some internodal bundles that brings the SA node impulse to AV node, so that AV node can transmit it down to ventricles. So in between ventricles and SA node, there is a channel called as internodal bundles that connects SA node to AV node, and from AV node there is another channel that connects the ventricle and AV node. So there it's kind of a 3-point: SA node, AV node, and Purkinje fibers. The bundles that connect SA node and AV node is called as internodal bundles, and the bundles that connect AV node and Purkinje fibers, the first segment is called as your bundle of His. It's a common bundle, the one big bundle that comes out from the AV node, and that's split into two: right bundle and the left bundle. And the left bundle again splits into two because left ventricle is bigger, so it has two branches. One is called as your left anterior fascicle, and the second one is called as your left posterior fascicle. So all these right and left bundles brings the electrical activity or these impulses down to the Purkinje fibers, and the Purkinje fibers is when they are activated, the ventricle contracts. This is how our electrical conduction system works. So SA node, from there we have internodal bundles that comes to AV node. The same time, SA node is connected to the atria through interatrial bundles, and from the AV node, impulse is down to bundle of His, right bundle, left bundle. Left bundle has two branches: anterior fascicle and posterior fascicle. This is technically the wiring of the heart is. And how the ECG is formed, and each part of ECG representing which part of this conduction system or which part of the myocardial electrical activity. When it comes to the SA node, at the moment when the SA node fires, the first area of the heart where the impulses reach is your right atria, because SA node lies in the right atria. So that's the nearest part. So right atria literally depolarizes first, and that is represented by the upslope, the first phase of your P wave. So when it comes to the SA node, when it fires, then you have your right atria receives the impulses first, and that impulses creates the right atrial depolarization, and that you can see the first half of your P wave. And when the electrical active impulse reaches the left atria, that's the second closest to the SA node, it travels through the interatrial bundles and it reaches the left atria. That forms your second half of your P wave. So your P wave in total represents atrial depolarization, and the first half is the right atrial depolarization and second half is the left atrial depolarization. So that's the P wave. But even after the right and left atrial depolarization completes, still your electrical impulses from SA node will not reach your AV node. So it takes another bit of time. So before we go to that, we will see what's the nature of the P wave. Usually the P wave denotes atrial depolarization, and the width of the P wave, or the time taken for the atrial depolarization, it's usually 80 to 100 milliseconds. In simple terms, if you look at an ECG paper, every single millimeter or every single small tiny squares, in the x-axis it denotes 0.04 seconds, and in y-axis it denotes 0.1 millivolt. So the time taken for the total atrial depolarization, or the width of the P wave, is usually 80 to 100 milliseconds, or in a graph paper it will be 2 to 2.5 millimeter in width. So within that time, in approximately in around 80 to 100 milliseconds, the impulse that is produced from SA node reaches the atria, but the internodal bundles, that is the road between the SA node and AV node, it's slightly slower than the interatrial bundles, and it takes a little bit more time to reach the AV node. That time period is reflected as your PR segment. That's the little segment in between QRS complex and P wave. So once the SA node fires, the impulse reaches the right atria first, then the left atria. So we have the P wave. Still the impulse hasn't reached the AV node. So you have usually an isoelectric line. That means a zero line until it reaches the AV node. So the PR segment is the segment between from the end of your P wave till the beginning of your QRS complex. And the total time taken for an impulse travel from an SA node to AV node, that is the P wave plus PR segment. So that is your PR interval. So when you have a PR interval, that means the interval from the beginning of the P wave, where the SA node fires, and the beginning of the QRS complex, where the impulse reaches the AV node, that time is called as the PR interval. That time period is called as a PR interval. So the PR interval, usually it should be less than 200 milliseconds, or on a graph paper it should be less than 5 mm, or a large square 5 mm. So that PR interval represents the total time taken for an impulse to travel from SA node to AV node. That's a PR interval. So if that prolongs, there comes your AV blocks. First degree, second degree, and third degree AV blocks comes in for this PR interval. Okay, so you know now the P wave and the PR interval. So the SA node fires, you have the right atria, then the left atria, so you have P wave completed, then the PR segment. In total, you have your PR interval. That time, at the end of the PR interval, you have your impulse reaches the AV node. As soon as the impulse touches the AV node conducts it down to the ventricles through the bundle of His, right bundle, left bundle, anterior fascicle of the left bundle, and the posterior fascicle of the left bundle. there comes your QRS complex. So once the impulse reaches the AV node, here SA node fires the impulse, then it reaches the AV node at this point. There you have your QRS complex that denotes the depolarization of your ventricle. And after when it comes to the QRS complex, it indicates the depolarization of the ventricle, and it should be less than 120 milliseconds. That means it should be less than 3 mm on an ECG strip. If it is more than that, you have some trouble in the conduction system within the ventricle. That means you have a bundle branch block. So it should be less than 3 mm, or it should be less than 120 milliseconds or 0.12 seconds. And the height of the QRS complex also is slightly significant at this level, but when it comes to the 12-lead ECG, it's really significant. Usual voltage height is around 0.5 to 3 millivolt or 5 to 30 mm. If it is more than 30 mm, usually that indicates a left ventricular hypertrophy. So, or sometimes if it's an S wave, it can indicate a right ventricular hypertrophy, but usually it indicates a left ventricular hypertrophy. But don't think about that at this stage, because this is just a rhythm analysis. Okay, so it should be less than 120 milliseconds. If it is more than 120 milliseconds in wide or 3 mm in wide, that indicates a bundle branch block. We will see in later chapters, we will see what a bundle branch block is. And after the QRS complex, what happens? After the ventricular depolarization, ventricle start to relax or repolarize. There is an early phase of repolarization that is called as your ST segment. From the end of your S wave till the beginning of your T wave, that segment is called as your ST segment. ST segment usually isoelectric, or any abnormality in the voltage of ST segment, there comes your myocardial infarction. So we will learn at that time. And that's your ST segment. Usually an ST segment, that's an early, that indicates an early repolarization of ventricle. And usual time for ST segment is around 5 to 150 milliseconds, or should be technically less than 4 mm in length. And after the early phase of repolarization, you have a late phase of repolarization that is denoted by your T wave. Your late phase of repolarization is your T wave, and the end of T wave is your end of ventricular depolarization and repolarization, and then it goes to isoelectric line. It waits until the next SA node firing to form a P wave. So usually the T wave is important as well. Therapeutically, clinically, it's really important. It comes in MI, it comes in electrolyte imbalances. So in so many things, you come across the abnormalities in T wave. The usual time frame for the T wave somewhere between 100 to 200 milliseconds or 2.5 to 6 mm. And the voltage in limb leads, it should be less than 0.5 millivolt, and in chest leads, it should be less than 1 millivolt, or 5 mm should be in between 5 mm or 10 mm. 5 mm in limb leads and less than 10 mm in millimeter in the chest leads. So that's your T wave. If in limb leads, if it is more than 5 mm, that's your high peaked T wave, or in chest leads more than 10 mm, it's called as your tall T wave. So these are the normal waves of your ECG. And there's one more thing, it's important in a normal intervals, that is your QT interval. Your QT interval is from the beginning of the QRS complex till the end of your T wave. The beginning of your QRS complex is actually the beginning of your depolarization of the ventricle, and ST segment is the early phase of repolarization. T wave is a late phase of repolarization. At the end of the T wave, your repolarization of the ventricle ends. So QT interval means the total time taken for the ventricular activity. That means the beginning of QRS complex, end of your T wave. The total time taken for the for your ventricular activity. So it's from here to here. So that's called as your QT interval. Normally a QT interval itself doesn't have much value. We have to correct it to a heart rate of 60. we have to apply some equations and make it into a heart rate of 60, normalize into a heart rate of 60, then the QTC, that's called as corrected QT, and that has the therapeutic value. There are 4 formulas available, but don't look at the formulas. You will get the QTC in your ECG. The QTC is automatically calculated by the machine, so you don't have to worry about the QTC calculation formulas. Or if you want to calculate, you can divide the QT interval by the square root of RR or 1/3 of the RR, then you will get your QTC, but the machine will do the calculation for you. The QTC is really important because if the QTC is prolonged, there is a chance that the next R wave may fall on a T wave. That's the problem with the QTC. That's called as R on T phenomena. R on T phenomena can cause a very complicated ventricular fibrillation, and that's really hard to revert back. So that's why the prolonged QT is always a worry in intensive care units. For males, the corrected QT should be in between somewhere in between 350 to 450 milliseconds or 9 to 11 mm, and in females it should be somewhere between 360 to 460 milliseconds or somewhere the 9 to 11.5 mm. So the QTC is calculated by the machine, so you can see the QTC straight away, and if the QTC is prolonged, you have to watch all the drugs what you're giving. Okay, so these are the major intervals, waves, and all on the normal ECG. So you can see here at the when SA0 fires, the P wave starts. The first phase of P wave is your right atrial depolarization. Second phase of P wave is your left atrial depolarization. Still the impulse didn't reach the AV node. Once the impulse reached the AV node, so the total time from the SA0 firing till the impulse reaches the AV node, that's called as your PR interval. Once the impulse reaches the AV node, you have your QRS complex, that's a ventricular depolarization. Then your ST segment, that's your ventricular early repolarization. Then you have your T wave, that's a ventricular late repolarization. So in some cases, you can have a small U wave, that's the late repolarization phase as well. That's very rarely you will see a small tiny U wave after T wave. And then the heart waits for the next SA node impulse. Once the next SA node impulse comes, then again the cycle restarts. The P wave, QRS, ST segment, T wave. The time between your T wave and your P wave is called as your TP interval. In case of a prolonged QT, what happens? The T can fall on this. The next R wave can, if the QTC is prolonged, the next R wave can fall on top of the T wave. That can cause your R on T phenomena and ventricular fibrillation. That's really hard to revert back. So this is all about your normal ECG. These are the normal characteristics, normal waves, normal intervals, and normal segments of an ECG. So when you have an ECG strip, what do you have to check? How will you make sure it's a normal ECG? You have to check for the P wave. Is it present? In a normal ECG, it should be present. Is it regular? In a normal ECG, it should be regular. And is every P wave followed by a QRS complex? In a normal ECG, every P wave should be followed by a QRS complex. And the rhythm is the ventricular rhythm is QR rhythm, the rhythm of the QRS complex and P wave, already we checked. And is it regular? In a normal ECG, it should be regular. And the rate, it should be between 60 to 99. If it is below 60, it's sinus bradycardia, and if it's above 99, that's above 100 and above, it is tachycardia. And the PR interval should be less than 200 milliseconds. If it is more than 200 milliseconds, first degree heart block, and then you have your second degree and third degree heart blocks. And the QRS width should be less than 120 milliseconds. If it is more than that, there comes your bundle branch blocks. And T wave, you have to look for, is it upright or inverted? If it is inverted T wave, again the myocardial ischemia, and if it's tall or flattened, you can you look at your electrolytes. And the QTC should be less than 450 in males and less than 460 in females. Any abnormalities in QTC, you will look at the you will check for the R on T phenomena, and you will look for the drugs that could prolong the QTC. Okay, this is all about a normal ECG. So here is the end of your chapter 1, the normal ECG characteristics. And in the chapter 2 of the unit 1 of dysarrhythmia, we will learn about the actual dysarrhythmias. Thank you for watching. Good luck.